Welcome to this presentation on the IMPATT diode in microwave engineering, presented by Professor Gottapu Sasibhushana Rao. This video explains its definition and structure, basic principle of operation, the origin of negative resistance, and the important equations and related problems. We will first see its definition and structure. Next, we will understand the basic principle of operation. Then, we will see why negative resistance is produced. Finally, we will discuss the important equations and a simple numerical problem. An IMPATT diode is a microwave semiconductor diode. It is mainly used as a high-power microwave oscillator. It operates under a high reverse bias voltage. Its typical operating frequency range is about 3 to 300 GHz. Its operation is based on two effects: avalanche multiplication and transit time delay. This figure shows the basic P+, N, I, N+ structure of an IMPATT diode. The P+ region is heavily doped. The N region acts as the avalanche region. The I region is the drift region. The N+ region is also heavily doped. As shown in the figure, the diode is operated with a DC voltage near or above breakdown and is connected to a microwave resonator. Microwave power is produced by the combined avalanche effect and transit time effect. This slide shows the basic operation of the IMPATT diode. A high reverse DC voltage is first applied near avalanche breakdown. A small RF voltage is then superimposed on this DC voltage. Impact ionization produces electron-hole pairs in the avalanche region. These carriers then move through the drift region. The avalanche process produces about a 90-degree delay. The carrier transit through the drift region produces another 90-degree delay. Together, these delays give approximately a 180-degree phase shift. This produces negative resistance and supports microwave oscillations. This slide explains negative resistance. A normal resistor absorbs RF power from the circuit. An IMPATT diode behaves differently. Under the required phase condition, it supplies RF power to the circuit. Therefore, the diode behaves as a negative resistance DEVIC. Why does negative resistance occur? There are two important delays. First is the avalanche delay. The avalanche current does not rise immediately and therefore lags the voltage. Second is the transit time delay. The carriers require some time to cross the drift region. Together, these two delays produce approximately a 180-degree phase difference between RF current and RF voltage. Because of this phase difference, the diode delivers energy to the microwave circuit. So, the 180-degree phase shift is the main reason for negative resistance. This slide gives the important equations of the IMPATT diode. The transit time depends on the drift region length and the carrier drift velocity. It is written as transit time equals drift region length divided by drift velocity. The operating frequency condition depends on both delays: the avalanche delay and the drift delay. Therefore, the total effective delay is related to the operating microwave frequency. Tau is equal to L Vd. Tau equals L divided by drift velocity. This slide gives a simple numerical example. The drift velocity and the drift region length are given. First, we use the transit time and frequency relation shown in the slide. The given values are substituted into the formula. From this calculation, we obtain the operating frequency of the IMPATT diode. This example shows how the physical drift region dimensions determine the microwave operating frequency.